When you do experiments to determine the reaction rate or the kinetics of a specific reaction, it is very important to show to yourself and to other readers that you thought about external diffusion and that you eliminated its effect on your reaction rate. External diffusion is a reactor-specific parameter, and you cannot use data that was generated while it was present in a different reactor system. So in this scenario, and it's also then important when you read other papers to make sure that they in fact paid attention to this phenomena, so that the rate equation that they published is in fact the true kinetics that you can use safely to design your own reacting system. So this researcher, for instance, considered just this reaction that where A goes to B, and it's in a batch reactor. All parameters were kept constant except the stirrer speed between two different runs. So it's at the same temperature with the same initial concentration of reactant A. At the lower stirrer speed, 500 RPMs, the formation of B was monitored by taking samples at different time periods, and this profile was observed. Everything else kept the same except a higher stirrer speed, and a profile that's indicative of a faster rate was obtained. So is the intrinsic kinetics different? No, that cannot be, because I've got the same catalyst particles there, I've got the same amount of catalyst, same temperature. So the only thing I can conclude is that the surface concentration throughout that run was higher than the surface concentration in the green run. So higher surface concentrations, and therefore I am measuring a higher effective rate. So if I should think about the surface concentration there, it is higher with the red run than with the green run. Whether I have reached the limiting case, where the surface concentration is pretty much equal to the bulk phase concentration with my 1000 RPM run, still need to be confirmed. I can only confirm that once I in fact choose a third run, where I have something like 1500 RPM in my batch reactor. If now I measure concentrations that pretty much fall on the same line, I have proven that even if I increase this RPMs, and by increasing that I increase my Kc, because I am decreasing the thickness of my viscous boundary layer. Even if I do that, I do not improve the rate even further, which implies that I've hit this limiting scenario where the Ca surface is equal to Ca bulk. So if I operate at 1000 RPMs, I already satisfied that condition. In a packed bed reactor, the presence of external diffusion effects can actually mean that for exactly the same catalyst mass and volumetric flow rate, therefore for the same tau or for the same weight hourly space velocity in my reactor, I can get different conversions based on the geometry of my reactor. And that does now not only mean that the Ergen equation affected my pressure and therefore the concentration of my reactants along the length of my reactor. So here in this second scenario, I have a long, thin reactor, so I've got a relatively high linear velocity, implying that I've got a high Kc value, which also means that along the length of my reactor, chances are good that Ca surface may approach Ca bulk. However, in this reactor, where I have a shorter fat reactor, I'm going to have a relatively low linear velocity, and according to the Turnus-Kramer correlation, that implies that I've got a lower Kc value. If I've got a lower Kc value, it implies that along the length of my reactor, Ca surface is less than Ca bulk. And the rate that I can actually measure is lower than that optimum rate that will apply when I have no external mass transfer limitations on my rate. In your first touch on this theme, you are actually required to explore exactly this phenomenon. And in this case, a design engineer specified a certain catalyst mass and he expected a conversion of 91% by assuming that the surface concentration is equal to the bulk phase concentration. In this third scenario, your intrinsic mass-based rate constant was actually an unknown, but you can use the expected conversion in order to integrate over the given mass of catalyst and then subsequently to solve for that intrinsic mass-based rate constant. Conveniently, in that you were told that it is a first-order reaction, so it's an actual first-order reaction, which implies a few things for our analysis. The first important thing, it's actually easy for a first-order reaction, if this rate constant is an unknown, to perform analytical integration and not our numerical technique. So then you can end up with an equation in which you can just substitute that 91% in order to calculate your intrinsic rate constant. Also, you know that by substituting CAS in terms of CA bulk, I can use the sum of resistances approach. And now that I have solved my intrinsic rate constant from the data published for where the engineer assumed no mass transfer, I can just use the information on the actual performance, integrate again in order to, with a new X value, but now with the effective rate constant as my unknown in my rate equation, in order to solve for K effective. Once I have K effective, I can use the sum of resistances in order to solve for my mass-based external diffusion rate constant. Another very important concept. Please pause first, take a sip of water and then delve into this next important part of this theme. Is the effect of temperature on this transfer of regimes between internal reaction rate control to external diffusion mass transfer control as a function of the operating temperature. It is therefore important for us, if we want to extrapolate data, to make sure that we know at which temperature our information was available in the first place. So if we once again consider our first order reaction and we say that we are in the regime where the reaction rate, the intrinsic reaction rate, controls the rate completely. In other words, our effective rate constant is also equal to our intrinsic rate constant. So for now, we are also focusing on a first order reacting system. Of course, with an increase in temperature, I would expect a very sensitive behavior in my rate. So the concentration in my reactor I now keep constant. So it's not as if this is going to be, it's like a CSTR, and you ensure that your concentration for each of the subsequent runs in your CSTR is exactly the same. Only difference between the runs is the temperature. So you will see for higher temperatures, I have a very sensitive rate expression because it follows that Arrhenius temperature dependence. That will be true if I have a first order reaction, and therefore if I calculate my overall resistance, I can neglect this resistance because this rate is so fast that this term pretty much goes to zero when I compare it to my internal or actual rate of my intrinsic reaction. Ca surface is equal to Ca bulk. However, when I am in the regime where external diffusion controls my rate, so for a first order reaction, my effective rate constant is equal to the mass-based external diffusion rate constant, or that resistance due to the intrinsic reaction rate is so low that that term falls away. It implies that my surface concentration pretty much goes equal to zero. And that implies that the rate constant that determines the temperature dependence of my effective or observed rate constant is actually that Kc. And as we have discussed previously, that is a very weak temperature dependence. So in fact, as we mentioned in previous slides, about temperature to the power of 1/6, and you would not be wrong if you actually neglected that and said, oh, that will actually then just stay pretty much the same. The implications of this is With an increase in temperature, these two resistances does not behave in a similar fashion. With an increase in temperature, the resistance to external mass transfer and this rate constant will remain relatively constant, whereas this rate constant will increase exponentially, and therefore this resistance will decrease exponentially. So the effect on my overall resistance or on my overall rate constant due to external diffusion will increase as I increase the temperature. Let us consider a specific scenario. Remember, we can only apply the sum of resistances approach when we have a first order reaction. So let's say at 300 Kelvin, I've determined that the resistance to the rate due to the intrinsic reaction rate is 5. So in other words, the inverse of that rate constant. And the inverse or the resistance to the rate due to external diffusion is also 5. In other words, both of them have about equal hold or control over my reaction. Both of them affects the rate, and therefore my overall K effective value can be determined, but that overall resistance I know must be equal to 10. This implies that I am in that regime where the surface concentration is not 0. It is also not equal to the bulk because both of these rate processes have an equal effect on the overall resistance to my rate. So let's say I now increase my temperature. I increase it from 300 and I don't have to even increase it by much. Let's say I increase it to 320 Kelvin. The implication is that this parameter will remain pretty much constant at 5. But this one, depending on the size of the activation energy, is going to, this whole term, this is going to increase exponentially, so this whole term is going to decrease exponentially, such that it may in fact at that lower temperature be equal to 0.2. So then what I can surmise is that my overall resistance is going to be equal to 5 plus 0.2. It is 5.2, and I can see that I am moving into a regime where the surface concentration is going to become pretty much equal to 0, and where the rate will be controlled by the external diffusion process. Reason being that the two rate constants have different temperature dependence relationships. So I can start in a regime where this one actually controls the rate because it's very low. So it will give me a very high resistance value. But as I increase the temperature very quickly, the resistance is going to drop and fall away. So I can actually move from a regime where I have reaction rate controlled to a regime where the mass transfer controlled, because this step cannot keep up with that effect of the increase in temperature on my Arrhenius-based rate constant.